Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to look at finding approximations to solutions to Laplace's equation in 2 and 3 dimensions. So in this topic we're looking at Laplace's equation. We're going to discuss the physical problem and its properties. We're going to examine the equation. We will consider boundary conditions in 2 and 3 dimensions, and we will approximate the equation by using finite difference equations. This is going to create a system of equations which we can then solve. Now, by the end of this lab, you will understand Laplace's equation in 2 and 3 dimensions. You will understand how to approximate the equation in 2 and 3 dimensions using finite difference equations. You will understand how solutions may be approximated using systems and solving a system of linear equations. Now, Laplace's equation, it says that the Laplacian of the function is 0 everywhere, at least within our boundaries. U of x is a function of n variables, where x is a vector. It can be 1, 2, 3, or an arbitrary number of dimensions, but we will be focusing on 2 and 3 dimensions in this lecture. Now, in 1 dimension, Laplace's equation simplifies to the second derivative being 0. U is a function of a single variable, and if you have a two boundary conditions, then the solution is simply a straight line connecting those 2 points. Now, if we're dealing with soap films on the other end, let's think about that. At any one point on the soap film, you can consider that the force being exerted is proportional to the concavity. The more concave a soap film is, the higher a force is to pull it down. The same thing with concentrations, thermal energy, and electric potentials. Basically, for a system to be in steady state, the forces must equal and cancel each other out at every single point. For example, we do not expect concentrations in or higher areas of temperature in the middle of, for example, a room. So in 2 and 3 dimensions, this is Laplace's equation, the sum of 2 partials. In 3 dimensions, it's a sum of 3 second partials. Now, as I said, when we're dealing with soap film, the force is proportional to the concavity. There is greater force here than there is here. Consequently, this will much more quickly push in on that region. If we have concentrations inside a solution, if it is in steady state, we do not expect a region of higher concentration anywhere in the solution where that concentration is higher than everything else around it. If it was in steady state, that wouldn't happen, because if there is higher concentration, we expect it to diffuse out. So there cannot be any region of higher concentration. If we're dealing with thermal energy, again, I don't expect the temperature in this room, assuming this room is in thermal equilibrium, I would not expect there to be a pocket of hot air or freezing air right here. We would have expected that heat to diffuse out or heat to converge on a region which is cooler. So once again, we do not expect any one point to be higher, strictly higher or strictly lower than all the points immediately surrounding it. Okay, we're going to see how this is done, and we're going to see how the equations actually show this. So given these 2 examples of Laplacian in 2 and 3 dimensions, let's approximate these using the divided difference approximations for partial derivatives. All right, so there's the second derivative, or an approximation of it with respect to the first variable, and here's the approximation with respect to the second variable. We can do the same thing in 3 dimensions, second partial with respect to the first, second, and third variables. Now, there's a common factor of h that we can multiply through, so let's multiply through by h and collect like terms, and then solve for the central point. So here we're solving for u of xy, and here we've solved for u of x, y, and z. Now, what do these 2 approximations mean? Well, in 2 dimensions, what is this saying? The solution to Laplace's equation is the average of the 4 points around it. So this value if u is actually a solution to Laplace's equation, this value had better be the average of the 4 points around it. In 3 dimensions, it's essentially the same thing, except it's saying in 3 dimensions. This value has to be the average of the points around it. If it is not, we are not in a steady state, and therefore we do not have a solution to Laplace's equation. But this is only an approximation. What does this mean in reality? Well, in reality, it means that if I have a point here, the temperature at that point had better be the average of all the points around it in the limit as that sphere converges on that point. Now, in 1 dimension, we can see this as well. The point in the middle is just the average of the 2 values around it. Now, to satisfy this constraint in 1 dimension, what did we need? Well, we had the real line, because it's only defined on a single variable, and we needed 2 boundary values. We needed a domain on which we were finding a solution to the problem. In this case, the only domain that can be bound in 1 dimension is an interval, the interval AB. In 2 dimensions, however, we're evaluating or approximating the solution in 2 directions. So therefore, we have to hit a boundary somewhere in every single direction we go. The only way that this can be done is if we have a domain that is closed by a boundary. Just like in 1 dimension, we needed to know what the value of the function was, what the boundary conditions were at the 2 endpoints. In 2, and we'll see in 3 dimensions as well, we need to know what the concentration or the value or whatever the value of the function is on the boundary. And we're denoting the boundary by partial of the domain. So we need to know what the constraints are. Those are given in the problem. In 3 dimensions, again, as before, we're going to have some sort of volume or some sort of domain in 3 dimensions, and in order to approximate Laplace's equation on the interior of that domain, we need to specify the value of the function along the entire boundary. And in this case, the boundary is the boundary of the entire cube on all 6 sides. Here's a few other examples. You could, for example, have a square on a plane. 3 of the sides are grounded, while this is at 100 volts. You could have a coaxial cable where the exterior is grounded and the interior is at 100 volts. Or you may have 2 thin films separated by a small distance, one at 100 volts, one at negative 100 volts, inside a container that is grounded. In all of these cases, there is a boundary. Here we even have a boundary on the interior, but we would like to find out what the solution to Laplace's equation, and therefore, in this case, what is the electric potential on the interior. Why do we want to find the electric potential? Any electron that is placed in that location will move according to the electric potential in that domain. Now, let's go to temperature, because temperature is often easier to think about. Here we have a cube. These 2 sides of the cube are set at 100 degrees. These 4 sides of the cube are set to 0 degrees. Now, technically, we don't really have a temperature along the boundary of those 2 sides, because you're having one boundary that's at 100 with one boundary that's at 0, or one surface that's at 0. But again, we don't have to have it at every single point on the boundary. But as you can see, we can actually approximate the temperature throughout the interior of the cube, and you will be able to do this by the end of this class, and you will find that dead center, the temperature is 33 degrees. Well, actually, it's 33.333 degrees. It's exactly the average of the temperature on the 6 sides. Now, as you move closer from the center towards one of the two warmer sides, the temperature warms up. As you move towards one of the four sides that is at 0, the temperature cools down in an expected rate. Similarly, let's say you have a cube where all 6 sides are at 0 degrees Celsius, and we have 3 heat sources that are continually radiating at 100 degrees. The sides are kept at 0. These 3 points are at 100 degrees. Well, within the vicinity of each of these points, you would expect the temperature to be close to 100. However, with only 3 points being warm, very quickly as you move away from one of these points, the temperature drops. This is the boundary of the region where the temperature is 2 degrees. So the vast majority of the room is cold. However, as you approach one of these points, you of course expect it to get warmer. And because you have 2 points, you expect some sort of interaction that is going to be caused by those 2 points being closer than, say, those 2 points. Now, how are we going to do this? Well, let's think about a wire frame first of all, and then we'll translate that wire frame into a real problem. But let's just take a wire frame. How would you define a boundary with a soap film? Well, you could take that wire frame, you could bend it, turn it into a loop. Then take that wire frame, bend it into some bizarre shape, dip it into soap water, take it out, and a film appears. As you can imagine, at every single point, you're going to have some sort of concavity due to the bizarre shape of the boundary. You're going to have concavity in one shape, and at that point you're going to have, if you look at the other direction, you will have a concavity that's equal, but in the opposite direction. Therefore, the 2 forces cancel each other out. Now, this doesn't really work with soap bubbles, because with a soap bubble, the soap bubble cannot contract to a point, because a soap bubble has an additional force exerting outwards. You have trapped a region of air, the soap bubble is pushing in, but then you have a force pushing out. So this is not Laplace's equation, but Poisson's equation, where there's a forcing function on the left-hand side of Laplace's equation. That you're going to probably see in one of your other classes. But it's still reasonable to consider. So how do we approximate a solution? What did we do with boundary value problems in one dimension? We took the interval and we divided the interval up into n equally spaced points. And we stated that, or we found that the distance between the points was h. In 2 dimensions, we're going to have a frame going around it. And we're going to take the grid, and we're going to break the grid up into, or the domain in 2 dimensions, we're going to break it up into a grid. So here we're going to break apart the domain. The size of the grid will be h. The distance between the points in the y direction will be h. The distance between the points will be h in the x direction as well. This is going to simplify the problem. We could use different values of h, but it just leads to messier, uglier equations that don't actually teach you anything else. If you're masochistic, you can try it, but you're going to see finite elements, which are a much better way of finding these solutions. So for example, given a point h, x, the next line will be x plus h. Given a line y, the previous one will be y minus h. Now, for simplicity and for clarity, we're going to use a few standard variables. Now that we're going to divide the plane into points, we're going to number each of those points. We're going to give each of them a number, and that means we will probably be iterating over them. To make it clear which direction, x, y, or z that we're iterating over. Our variables we will use will be ix, iy, and iz. And the time dimension, just like previously, will always be k. So here we have a rectangular domain in 2 dimensions. This makes life a little bit easier. So the boundary conditions would be defined on the edge of the rectangle. The question then is, what is the solution on the interior? Well, we're going to take that domain, we'll cut it up into a grid. These points are on the boundary, and then we have a whole bunch of interior points. Now, the size of the domain will be n sub x by n sub y. We are again going to ensure that h is the same in both directions. Now, taking away the grid and just leaving the points, this seems to be a reasonable object that we can approximate using a matrix. So here we have points in the matrix that represent points on the boundary, and then we have all these points in the matrix that are unknown. They're on the interior of the domain, and we're going to have to try to find approximations to those points. Alright, so we have the boundary values. These boundary value problems, or boundary values, must be given in the problem. They're not unknowns, they're not random. We have to determine what they are. We are given what they are. It's the points on the interior that we're going to approximate. And we have, in this case, 4 by 2, 4, 6, 7, 28 points on that interior. Now, how are we going to approximate? What we're going to do is we're going to, at each interior point, just like we did with boundary value problems, create an equation, a one equation in the other variables, including the point. That's going to give us, in this case, 28 equations and 28 unknowns. So focusing on this point here, here's the interior point. How are we going to approximate Laplace's equation at that point? There's the interior point. Well, this is Laplace's equation. Now, specifically here, U34 is the point where x equals 3 and y is equal to 4. So let's substitute x equals 3 and y equals 4 into Laplace's equation. Alright, there it is. We've brought one side over, multiplied both sides by 4, and now we have x3 minus h, x3 plus h, x4 minus h. How do we deal with those? Well, remember that x3 minus h is x2. x3 plus h is x4. y4 minus h is y3, y4 plus h is y5. We can substitute all of them into that equation. So let's replace y3 minus h with, or sorry, x3 minus h with x2 and so on. So therefore, there's our simplification. And recall, because we're trying to approximate the solution, we're approximating the value of the function at this point by this entry in the matrix. So let's replace each of these with u2, 4, and so on. Now we have an equation that depends on these 5 values. It's linear, and therefore what we were expecting. Let's take a look at this point here. This point has one of the 4 boundary points, or surrounding points, on the boundary. So what do we do here? This point is a boundary point. We've substituted, gotten the equation, but that's a boundary value. A boundary value is given. If it's given, that means it's a value that is not an unknown. Let's take it to the other side. So now we have an equation in 4 unknowns, these 4, with a right-hand side that in this case is probably non-zero. We're going to do this same operation at every single interior point, always writing down an equation, a linear equation, and then determining how many of those points are actually on the boundary, in which case we'll bring those to the other side. This is going to give us a system of equations. We will solve that system of equations, and that's going to give us approximate values to the solution to Laplace's equation on the interior. Here we have 28 equations, 28 unknowns, and all boundary values must be known, otherwise it won't work. In 3 dimensions, it's almost the same, except now we're going to have an equation with 7 terms, an interior point, and 6 points around it. And we will have to create one of those for each point in the interior. If we can find that, that's quite nice. Find a solution to Laplace's equation, not a problem. Solve a system of equations, and you get approximations. Now, the grid that we're looking at before had perfectly fit a rectangular boundary. Most things in the world do not have regular boundaries, or at least not rectangular boundaries. You might get lucky, but unlikely. You might have spherical boundaries or irregular boundaries. How are we going to approximate a solution to Laplace's equation on something other than a nice rectangular boundary? Like, for example, you might have this shape appearing. Well, we could try to impose a grid over it, and then we'll notice that some of the points fall on the interior, other points fall outside of that domain. If our grid is not good enough, we could extend it, but in this case, here we have points that are exterior and points that are interior. If we made the grid twice as fine, so halve the value of h, there are now more points, and notice that the boundary does slightly more closely match the boundary of the irregular shape. You could even use symmetries in the problem, but in most cases what we're going to see is that finite elements make a lot more sense, and finite elements will later on allow us to fit this shape more simply. But in this case, we're looking specifically at using finite differences. So finite elements was a technique that was pioneered by Alexander Khrennikov, and he was a civil engineer, and Robert Current. This was in the 1940s. They were trying to model a bending beam or bending surface. And what they did is they used tessellations. Rather than using a square grid, they used triangles and tessellations to try to fit the shapes. Nanotechnology students are actually going to see the finite element method in their 3B term. But let's go on and let's just at least try to find an approximation using a grid for this example. Here we have 16 points on the interior. All the remaining points are considered to be on the boundary, and we don't care what their values are. All we know is that they are given. It's the points on the interior that we want to approximate. We want to create a system of n equations in unknowns, and in this case there's 16, so it's going to be 16 equations and 16 unknowns. So let's label each interior point by a value, w1 through w16. Now, w1 is associated with the point in the matrix u22. w10 is associated with the point u47 in the matrix. So what we're going to do is we're going to set up a system that is 16 by 16, and we will determine, like for example, u46 is w9, but it's adjacent to u56, which is w14. So w9 and w14 will be considered adjacent, and we will create our system of equations using those. Now, let's get some boundary conditions. Let's say this is 5 volts, this is negative 5 volts, and everywhere else here is 0 volts. So, 0, 0, 0, 0, unknown, 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 unknown. These 5 here are considered to be 5 volts. These 1, 2, 3, 4, 5, 6 points will be considered to be at negative 5 volts. Everything in purple is at 0. Those are our boundary conditions, and given those boundary conditions, we will approximate the 16 points on the interior. Let's see how we're going to do this. Notice that any point is either unknown or has a boundary value. So let's actually take a look. Here's Laplace's equation, or at least a finite difference approximation, and we have a point in the middle, and for each point we're going to look at the 4 points around it to create such a linear equation. So let's zoom in on the top left-hand corner. Well, taking a look at this one point, W1, we notice that it's the sum of the 4 points around it minus 4 times W1. So that's going to be negative 4 times W1 plus 5 volts, plus 5 volts plus W3 plus 5 volts plus W2. We can bring the two constant terms onto the right-hand side, and that gives us negative 4 times W1 plus W3 plus W2, that's equal to negative 10 volts. There's our first equation. Taking a look at the second point here, what do we have? We have negative 4 times W2 plus 5 volts plus W4 plus W1 plus, this is 0 volts here. So this boundary value is 0 volts, this boundary value is 5 volts, and so we can bring the 5 volts over, and now we get a second equation. Taking a look at this point, what do we have? Negative 4 times W3 plus W1 plus 0 volts plus 5 volts plus W4. Bringing the constant terms to the right-hand side, we get a third equation. And finally, here we have a point that's entirely on the interior. And so now it's just W2, negative 4 times W4 plus W2 plus W6 plus W3 plus W5. We're going to write down such an equation for every single interior point. Given that set of equations, we're now going to create a system of linear equations, a matrix and a vector. Here's our matrix, here's our vector of unknown W values, and here is our right-hand vector. We have to solve for the unknowns. Well, in this case, if you were to type all of this into Matlab, you would get the following values: 3.7848, a couple of values close to 0, and everything here seems to be negative. Now, we can go back. W1 was located here. W2 was there. W11 is here. W11 is around negative 3.8164, which is really close to negative 5, at least as an approximation. In reality, in the actual world, this is very, very close, but because we could only approximate it, the distance to those boundary points was slightly further. So it's not as good an approximation as one would expect. This close to a boundary at negative 5 volts should be much closer to negative 5 than is negative 3.8. But now we can substitute all those values in, and we get an image as to what the electric potential might be. And again, the electric potential will tell you where or the path that positive charge will follow. As before, we also considered insulated boundary conditions. How did we do that? Well, remember that at an insulated point, what did we do? Well, the derivative at an insulated point is 0. We set an approximation of the derivative, a finite or a divided difference equation, approximation of the derivative. We would set it to 0. And if we used a very simple approximation, we saw that if you're very close to an insulated point, then the temperature there should be equal to the temperature close to it. So we're going to assume that if a point is insulated, its actual temperature is very close or equal to the temperature next to it. So let's say instead of having these points in purple being 0 volts, let's say that they're insulated. So now we have 5 volts here, negative 5 volts, everything else is insulated. What is the electric potential on the interior? Well, let's take a look at this point here. Negative 4 times W2 plus W5, 5 volts, plus W4 plus 1. Oh, wait a second. That's the insulated point. Well, remember what the assumption was. The assumption was that the value here equals the closest point. So we're going to assume that this value is equal to W2. It's a rough approximation, but it actually does work. So now we have this positive W2 canceling with one of these. Now the equation is negative 3W2 plus W4 plus 1 equals negative 5 volts. At this point, insulated, not insulated, and both interior. Again, negative 4 times W3 plus W1 plus an unknown. Plus 5 volts plus W4. What's the unknown? Well, we're going to assume that this point takes on the value W3. And so we'll substitute W3, and now once again, this W3 cancels one of those. We're left with negative 3W3 plus W1 plus W4 is equal to negative 5 volts. We're going to do this at every single interior point. And you're looking, oh my goodness, here's a negative W3, here's a negative here's negative 3, negative 2, negative 2, negative 3, negative 4. This is going to create an even more complex, or at least a matrix that appears to be more complex. And if we solve this matrix, we get the values at the interior points. So now, just as we did before, we can map. W6 is approximately at 1.87 volts. Now, here we have 0 volts, here we have insulated boundaries. Notice that at 0 volts, these points here are all very close to 0. If we have insulated points, they're not as close to 0. So again, here we have much more a smooth gradient from negative 5 going up to 5. Here we quickly drop to 0, stay around 0, and then go up to 5. All right, so you're thinking, we've got to come up with that matrix every single time for different boundary values, so we have to number them all. How are we going to do this? Well, we're going to see that we can actually do this in a nice mechanical fashion. And we're going to be able to make the Matlab do all the work for us. So first we have to allow the user to specify various boundary conditions. So you might have a shape that's irregular. How do we allow the user to specify it? Well, the user is just going to pass in a matrix. That matrix will have values on it. Any value that is finite and real is going to be assumed to be a boundary value. Any insulated point, we're going to use not a number to specify it as indicating that it is an insulated boundary point. And at every single point where we actually want to find a solution to the equation, we will assign it the value negative infinity. So for example, here we would pass in this matrix. It's a 6 by 9 matrix. These 5 entries are set to 5. These 6 entries are set to negative 5. All these points on the interior are set to infinity, negative infinity, and all of these are set to 0. Negative infinity indicates we want to find a solution at that point. If these points were insulated, then we would simply set all these points to not a number. Everything else would be the same. Now, how do we proceed? As with anything, we have to check boundary conditions first. If the boundary conditions don't make sense, we cannot solve the system. So in this case, for example, what we have to make absolutely sure is that every point on the boundary of this matrix must be either a finite value indicating a fixed boundary condition or not a number indicating that it is an insulated boundary condition. So the first thing you're going to be doing as soon as the arguments are passed in, the user is going to pass in the matrix, is you will check the entire boundary and make absolutely sure that all the points are not negative infinity. We can have a negative infinity on the interior, or we can have different values on the interior, it doesn't matter. But the only negative infinities must be up here in the interior. The second and third steps are our initialization steps. This is basically where we're going to take all of those points on the interior that are at negative infinity and map each one of those points onto a value, onto a number between 1 and m. We're going to count them. There's going to be m points, and we'll determine where they are. Now, this step is more or less done for you. I'm going to explain what's happening, and you have to understand the code, but at least let's see what's happening. Here we're getting the size of the matrix. We're creating an output matrix. The output matrix is just going to be a copy of the input matrix. Now we have to go through, you of course are going to be checking it for your boundary conditions, right? That's your error checking. But anyway, once we've done our initialization, now we have to associate each negative infinity with a number between 1 and m. Well, we don't even know what m is. So what we're going to do is we're going to set m to 0, and we're going to create two matrices. One is a mapping from U space to W space, and one is going to be a mapping from W space back to U. How will we do that? Well, U to W space is going to be initially a matrix of zeros. Every time we find a point that is negative infinity, we will assign that point in this U to W matrix with its number from 1 to m. To go back, we're going to do the opposite. We're going to have m columns in a matrix, and that each column entries will be the coordinates of the corresponding I sub x and I sub y within the original matrix. So basically we set m is equal to 0, go through all of the x values, go through all the y values. If one entry is set to negative infinity, increment the number of values of m and update these two vectors or matrices. The fourth step in the initialization is to create a matrix that is going to be used to solve our system of equations. For good reasons, we're going to use sparse matrices, and I'm going to describe this later on. But right now, here's the code for creating a sparse matrix that's relevant to our problem. We're also going to create a right-hand vector b, and that's going to be an m by 1 vector, so an m-dimensional column vector. Now, let's say that the user passes this matrix in. After we do our initialization step, the U to W matrix will look like this, and the W to U matrix will look like this. Why is it that way? Well, we've gone through here, and stepping through, we find that, oh, we have a negative infinity here. So we'll set this as the first point that's at negative infinity, and the first point, if we want to know where it's located, is 2, 2. Going through as well, the next point here is negative infinity at this location. So at this location we'll put 2 for the second point that we found that was negative infinity. And we will store the location 2, 3 in the second column of the W to U matrix. Third point, and it's at location 2, 4. Fourth point, and its location is 3, 2. The fifth point is at location 3, 4. So these two matrices are going to allow us to go back and forth. If we have a point in the matrix, we know which of the n equations or unknowns it's associated with. If we have the fact that it is the 7th unknown, we can go to the 7th column of this matrix to find out where that point was in the original matrix. That's what these two matrices will allow us to do. Now, the next step is we've actually got to fill in these matrices and vectors. How are we going to do that? We're going to update them by looking at each of the points. So here we're going to go look at our first point. The first point is at location 2, 2. So I'm just going to assign that to C temporarily. So the first point is C22. What are the neighboring points? Well, I need to go to the neighboring points from C22 to here, 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 here. Those values will allow me to create my system. So 5 is this point here. And so notice I'm just adding or subtracting a vector of either 1 or -1 and 0 in each case. That allows me to find my 4 neighboring points. Now, I've got my point. I know where it's the first point. I can calculate where it is by entering in or getting the appropriate entry in the V to U matrix, looking in the first column. And now I can also find the location of the 4 points around it. So now I'm looking at the 4 points around it. What am I going to do? Well, if one of those points is an insulated point, we're going to do nothing. An insulated point does not affect the value. A Dirichlet boundary condition, on the other hand, means that it's a boundary, it's a fixed value. And so what we will do is we will subtract 1 from the ith diagonal. So looking at the ith point, we're going from 1 to the last value of m. We're going to subtract 1 from the ith entry along the diagonal of m, and we will also subtract the Dirichlet value from the ith entry of the vector b. If it is also an unknown point, that means that we can figure out which unknown point it is. Let's say we find out that it's the jth unknown point. How do we get that? We go from the U to W matrix at that location, and because it's negative infinity, we're guaranteed that that is in the U to W matrix. That entry is also storing in that matrix the index, so the value j, as to which unknown it is. In this case, we will subtract 1 from the ith diagonal of m, add 1 to the ijth location in the matrix M, and we're going to do this for each of the 4 neighboring points. So, for example, here's C, it's 2, 2, it's the first one we're looking at. The first point is C plus -1, 0, this location. We notice that it's a Dirichlet condition. It's a Dirichlet condition, so we subtract 1 from the diagonal, and we subtract the Dirichlet value, the boundary value, from the vector in the first entry. All right, that's our first point. Let's go to the second point. Adding 1, 0 gives us this location here. It's negative infinity. It's negative infinity, so we can go to this matrix and determine that it is the 4th unknown. So we will subtract 1 from the diagonal, in this case 1, 1, and we will also add 1 to 1, 4. So we're starting with the first value, so 1, 4. Here we have not a number. That's the easiest condition. We do nothing. Finally, here we have negative infinity. It's another interior point. That means that we are looking at the second unknown. If we have the second unknown, then we add 1 to 1, 2. We subtract 1 from the diagonal in the first column. And so now we have -3 times W1 plus W2 plus W4 is equal to -5. That is our first equation. Now, if we repeat this at every single interior point, and you can try this if you want, we will end up with the following matrix and vector. With that, we can now solve that system. M\u, this gives us all the values or approximations of the values at the interior. And now we can use the W to U matrix to say, oh, wait a second, this first value should be stored at entry 2,2. This second value should be stored at entry 2,3. We'll copy it over there. This value should be stored at 2,4, 3,2, and 3,4. That is the matrix that we will pass back to the user. If there happens to be not a number, we're going to leave it as is. So, step 4 is to create and solve the system of linear equations. We're going to create a system of, or a sparse matrix, and we'll deal with that, I'll explain that later. And so essentially we're just going to go for k going from 1 to m, get the coordinates of the kth point for each of the 4 adjacent points, perhaps 6 if we're dealing with 3 dimensions, update the matrix as necessary, solve for w, and then once we've solved it, for each of the interior points, we're going to copy the values back into u sub out. So, for example, here is the matrix that we would pass in to Laplace 2D. So this sets all of these points to 0, all of these points to 5, and all of these points to negative infinity. When we get the output, we can call mesh. Notice that we have 5 degrees here, negative 5 here. Very quickly, there's a domain in the interior that is very close to 0, and then from here, the electric potential goes positive in that direction, smooths out, and drops. If we had insulated boundary conditions, here is the solution, and notice that the transition is much more gradual. It's a much smoother transition from 5 volts down to negative 5 volts. All right. In 3 dimensions, we can't use a matrix. We need more than a matrix. So basically, we're going to discuss how to create arrays, or 3-dimensional arrays, and we're also going to be able to visualize them with the function isosurf. In this case, isosurf will map out 30 surfaces that are of equal value throughout that matrix. So here, we're going to create an array of size 3 of 4 by 4 by 4. We're going to set one side to be temperature 1, one side to be temperature 4, its opposite side to be temperature 4, another side to be temperature 2, its opposite to be 5, 3, and 6. You're going to also write the function Laplace 3D. You're going to pass this 3-dimensional array in, and when you get the output, you're going to fill in the intermediate values. Now, your colors might vary slightly, but you will actually be able to rotate that cube and see how the values differ from one side to the other. And you should expect an appropriate change based on just your intuition and what the change should be if, say, for example, these were temperatures. Same thing here. You will be able to do the following. Create a 15 by 15 by 15 array, a 3D array. One side is 100, the other side is 100. These two ends are at 0. These two ends are at 0. Once you finish calling, you should get something that looks approximately like that. Now, isosurf is available for download from the lab directory. Here we have one surface at 100, one at 0, one at 50, and the remaining 3 that are closest to us, visually speaking, are insulated. And you can see that as you move from 100 to 0, you get a gradual transition. Here, this plane is at 50 degrees, as is this entire surface. And as you transition or move from this point up here, you get a transition from 50 to 100. And finally, here we have one surface that is set to 0, one point that is set to 100, and all other 5 sides are insulated. All right, is this what we expect? Well, yes, close to the surface, you do not expect significant change. However, as you get closer to this point, notice that this is the surface of temperature 16. Here's the surface of temperature 30. Here is the surface, and you can see that that surface sort of dips down a little bit, of temperature 10. Now, during the lab, you are going to implement Laplace 2D and Laplace 3D. Once you have Laplace 2D working, Laplace 3D only requires you to add one more loop. So I would strongly suggest that you do not start working on Laplace 3D until you have Laplace 2D working in all cases. After that, you're just making functional changes, adding an extra loop here or there, not much else, maybe a few other changes, but that's about it. And that will give you the solution to Laplace's equation in 3 dimensions. So your steps are argument checking initialization, mapping the unknown points to a unique number from 1 to m. This is whether or not you are in 2 or 3 dimensions, creating and solving a system of linear equations, and substituting those values back into the solution. Here's some useful Matlab instructions that you will probably want to use. What happens if you have a for loop, but rather than having a vector, what happens if you have a matrix? Well, what happens is, notice that this is a 2 by 4 matrix, and what Matlab does is it doesn't go through every entry of the matrix. Instead, it passes back columns. So, first time, I get the first column, 0, 0. Second time it iterates through, V is assigned 0, 1. Then it's assigned 1, 0, and 1, 1. In 3 dimensions, let's see, we have a 3 by 3 matrix. The first time, V is assigned the first column, 1, 4, 7. Second time, V is assigned 1, 2, 5, 8. And on the last iteration, V is assigned 3, 6, 9. Creating matrices that are in higher dimensions is more or less the same. Use the same constructor, zeros, except now you pass 3 dimensions. Now MATLAB tries really hard to print it out in a way that you can at least try to understand what's happening. So these are all the entries in the first 2 dimensions where the third value is 1. This is all the entries where the third value is 2, and all the entries where the third value is 3. As you can imagine, this gets really ugly if you, say, have a 20 by 20 by 20 matrix, or array, because then you will essentially see 20 by 20 matrices. Now, size will return as expected. It's 3 dimensions. And in fact, you can ask what the size is. NDims gives you the number of dimensions. Now, you just have to remember that NDims for scalars, vectors, and matrices is always 2. MATLAB treats scalars, vectors, scalars as 1 by 1 matrices, vectors as n by 2 matrices, and matrices are matrices. So all of these have 2 dimensions, even though this should have 0 dimensions and this should have 1. But again, from MATLAB's internal design, and it's a good design, scalars, vectors, and matrices are implemented as matrices of the appropriate size. Why are we using sparse matrices? Basically, you're going to be creating matrices that are as large as 100 by 100, where almost all of the entries are 0. If you try to solve such a system, it gets very expensive very quickly, because solving a system is an n by n system is order n cubed. If you have a sparse matrix where most of the entries are 0, you can significantly reduce the solving time. So this allocates memory for a sparse matrix that is 1,000 by 1,000, and we're going to reserve memory for up to 5,000 non-zero entries, at least initially. If you assign more than 5,000 entries, and that's not that hard because it's a million by a million, it has a million entries in it. If you go over, then it will allocate a little bit more memory for you. But in this case, we have a 1,000 by 1,000 matrix, and it has 5,000 non-zero entries. What's really cool, however, is that you don't have to do anything else. The internal representation is different, but the interface is the same. Here, I allocate memory for a sparse matrix that's 5 by 5 with 12 non-zero entries. Here, I have a zeros matrix that is 5 by 5. I'm just going to assign to various entries within the matrix. Here, I'm going to assign to the same entries, but in this matrix. Here, because it's a sparse matrix, it assumes you don't want to see everything. It assumes you only want to see the entries that are non-zero. So it will explicitly say, at location 2, 3, there's a -1. At location 4, 5, there's a value of -3, which is what we assigned here. 5, 5 is 9, is there. With a matrix that's built in the standard routine, we assume that it's dense, and so we'll just print the matrix. So these two are equivalent. But what's really beautiful now is if you call backslash on, say, 1, 2, 3, 4, it will solve this system of linear equations using sparse methods. But that's going to be the exact same answer you get if you have this dense matrix and call a solver, and notice we get the identical answer. So as far as you're concerned, you don't have to do anything else. You can assign to the entries in the same way, and the solutions are the same. So there's no skin off your back. You don't have to do any significantly more work, except you have to call the appropriate constructor. So in this case, we've looked at solving or approximating solutions to Laplace's equations in 2 and 3 dimensions. We looked at the physical problem, and we considered how we could actually solve it in 2 and 3 dimensions. What are its effects? We found a finite difference equation that approximated Laplace's equation in 2 and 3 dimensions. We created a grid, and some of those points in the grid were interior points. We numbered them, enumerated them from 1 to m. We set up a system of m equations and unknowns, solved that system, and substituted those values back into the matrix, which we then passed back. So, good luck with your lab, and all the best. Cheers!